Hey guys, welcome to your first lesson in chapter 6. Yes, we skipped chapter 5. We will get back to it later, don't worry. Alright, your objective with this lesson is to be able to write and graph exponential growth and decay functions. So that's what we're going to focus on. Alright, so by the end of the lesson, to know if you're successful, you should be able to identify and graph exponential growth and decay functions. You should be able to write exponential growth and decay functions. And you should be able to solve real-life problems using exponential growth and decay functions. All right, so let's get started. So we're going to start off by talking about exponential function. So an exponential function has the form y equals a times b to the x power. So it has to have a variable in the exponent. That's how we know it's exponential. If it just has a 2 or a 3 or a 4, that is not exponential. That is squared or quadratic, cubic, quartic, and such. So it has to have a variable. And a cannot be 0, because if a is 0, then the whole thing's canceled out. And the base b is a positive real number other than 1. All right, so it has to be a positive real number besides 1. And if a is greater than 0, so if your a amount is greater than 0, then that would be considered an exponential growth. If your a is greater than 0 and your b is greater than 1, then y equals ab to the x power is an exponential growth function. And the b part is called the growth factor. So that is going to tell us how the exponential function is growing. So the simplest type of exponential growth function has the form y equals ab. So this just means that, or not ab, y equals b to the x. All right, this just means there's no a value. That is like basically your parent function. Okay, so let's look at some examples of exponential growth and exponential decay. All right, so right here, where b is greater than 1, the parent function for the family of exponential growth with the base b, the graph shows the general shape of the exponential growth function. This right here, I need you guys to, hopefully you're listening, is very important. This is a new vocab word. It's called asymptote. All right, asymptote. It is basically where your graph approaches. It gets closer and closer and closer. So in this situation, it's getting closer and closer and closer to here, but it never touches and it never crosses. All right. Again, it gets closer and closer to the asymptote. It never touches. It never crosses. I had put that on the notes, but I just realized it's not on these. So hopefully by the time I get your copies made, you'll have the right one. All right, so new vocab word. You will hear me throughout this lesson use this word a lot, so it's important that you know what it means. All right, and then you see they give us the end behavior right here. As x approaches negative infinity, f of x approaches 0. So this is different than what we have learned in the past, because f of x is not approaching negative infinity because it's staying right here. All right, so it's getting closer and closer to 0. Now this part would be it's growing up to positive infinity for both, so this end behavior would be as x approaches positive infinity, f of x approaches positive infinity as well. So a little bit different in our end behavior than we have had in the past. So that's growing. Remember, we read left to right, so it's starting from the left and it's growing up. All right, this one we see that it is going down. So again, we have an asymptote. And the end behavior for this one is as x is approaching positive infinity, so it's going this way in positive. F of x is getting closer to the asymptote, so closer to 0. All right, and then on this side, it's growing up to where x is negative, so negative infinity for x, and f of x is positive infinity. Maybe you see where they have now switched it up. I've gotten asked a lot of questions. Does it matter if I put f of x first or x first? And I've told you guys it doesn't matter. Big Ideas has now switched it up on us. Go figure. All right, so right here, this is important because we tend to hate domain and range. But in this case, your domain is all real numbers. Why is that? Because it's going to negative infinity on the x, positive infinity on the y. So it's going in both directions. So this one's continuing to negative x. This one's continuing positive x is what I meant to say. In this case, your range is your asymptote. So whatever your asymptote is your range. So it changes, it changes based on the asymptote. In this case, our asymptote is the x-axis, which is where y is 0. So had this been like -1, then your range would be greater than -1. All right. Again, even for a decay function, your domain is all real numbers. The range is y is greater than 0. This number does change based on your asymptote. So it is important to be able to determine what your asymptote is. All right. So if your, I didn't put this on there either. Goodness gracious, lady. If your function is between 0 and 1, so not negative, but between 0 and 1, because negative, remember, means a reflection. That would be an exponential decay. So greater than 1, it's a growth. Between 0 and 1, it is a decay. All right, so you may want to highlight that part. So where b is greater than 1, it's a growth. Where b is between 0 and 1, it is a decay. All right, you just need that information. I know we're a few minutes in and we haven't done any math problems, but that was important information that you need. So now let's get to the math problems. All right, we are going to graph exponential growth and decay. Yes, you are able to use your graphing calculators in class, but you should know how to graph from scratch as well. All right, they gave us a table. They want us to input the values. So how do we input the values? Same way you would with any other. We just have 2 to the x power. So we're just going to replace the x with -2 and solve. So if we put in 2 to the -2 power, remember that's the same as saying 1 over 2 squared. Because if you have a negative exponent, if you remember your rules from pre-algebra and algebra, if you have x to the -a, then that is the same as 1 over x to the a. All right, so hopefully you remember that if you took pre-algebra. If not, you learned it in algebra as well. So then that becomes 1/4. So when x is -2, y is 1/4. And we're going to do that for all of them. So if you want to pause the video, plug them in, see what you get, and come back and see if you got the right numbers. Okay, another rule from pre-algebra algebra that you may have forgotten is that when you have x to the 0 power, anything to the 0 power equals 1. So this one right here, if you plugged in 0 for x, you would have gotten 1. And then if you plugged in 1, you would have gotten 2, 2 you would have gotten 4, and 3 you would have gotten 8. So we're going to go ahead and graph these points on the graph. So go ahead, pause, and graph them real quick. All right, so you would notice that this was going to get closer and closer and closer to the x-axis. It is not going to cross it. So your end behavior, this is an exponential growth. Our value of b was greater than 1. So if you want to look back above for your end behavior, you can. I'm going to write it here for you. So our left side is as x approaches -infinity, f of x is approaching 0, because that has our asymptote on this side. All right, and then as x approaches positive infinity, f of x also approaches positive infinity. And guys, remember, f of x, y, same thing. All right, I'm going to draw a line down there to separate those. All right, so now we have a b value that's between 0 and 1. So because our b value in this one was 2, we knew it was a growth. Our b value in this case is 1/2, so that tells us it's going to be a decay. So our graph should go down, our asymptote should be going this way. All right, so same thing, we're going to plug in our x values to get the y. All right, so we have -3. We're going to plug in -3 here. So this does get a little tricky. All right, because of the negative 3 being your exponent, that kind of switches it. So like how this one went down at the bottom, this one's going to move to the top. So it kind of makes it 2. All right, I'll show you what I mean. Okay, so I'm going to do this over to the side here. I'll zoom in a little bit. So what I meant is, okay, we have 1/2, and you are raising it to the negative 3 power. So you're saying like 1 to the negative 3 over 2 to the negative 3, because remember you have to distribute that exponent to both. Well, we can't have a negative exponent, so they basically like switch their sides. So the 2 to the 3rd comes up here, 1 to the 3rd goes down there. Well, we don't really care about 1 to the anything power because it's just going to equal 1 every single time. But 2 to the 3rd does equal 8. So this becomes 8 over 1, which equals 8. You can also put this in your calculator. All right, I'll show you that as well because I do have the fancy graphing calculators. All right, so if you put in, so remember parentheses are important. If you put in 1 over 2, oh, I didn't mean to, what? No, clear, 1 over 2, there we go. And raise it to the negative 3rd power. It will also give you the answer. So if you struggle with these, just know that you can put it in the calculator as well. So for example, let's plug in negative 2. So we do 1 over 2. Just remember your parentheses, because if you do it without the parentheses, it's only going to give the exponent to the first one. All right, and then we're raising it to the negative 2 power, and that equals 4. All right, so if exponent rules are not your specialty, this is something that you can do. And so then, if you guessed it, negative 1 is going to be 2. And again, if you plug in 0 for any exponent, it equals 1 every time. So 1/2 to the 0 power equals 1. All right. And then if we put in a 1 there, we would get 1/2. And if we put in a 2, we would get 1/4. So notice these are kind of inverses as far as the graph goes. So now we're going to plot our points and draw our graph. So take a moment, you can pause and do that. All right, so you should have gotten those points. All right, it's going to continue to go up on that way, and then this one's getting closer and closer to 0 without ever touching or crossing. All right, so our end behavior, you could look above for the end behavior. If you look above here, it's got the decay end behavior. It is as x approaches negative infinity. So this way, x is going to negative infinity. Y or f of x is approaching positive infinity. Then we have as, so we're going this way, as x approaches positive infinity, f of x or y is approaching 0 because it has an asymptote. All right, so with these next, I'm going to give you some self-assessment questions. I'm not worried about you graphing them at this time. Unless you want to give it a try or you want to put it in Desmos just to see what it looks like. But what I do want you to do is question 1 and 2. I want you to determine if the function is an exponential growth or decay, and then describe the end behavior. So we're just looking at question 1 and question 2. Is it an exponential growth or decay? And what is the end behavior? So please write that in your journal now. Okay, so the first one was a growth, the second one was a decay. I did fix this to be y because in our equation it's y. In this one it's f of x. So I did change this to reflect that. Where did I get this information? From your notes. Right here, we highlighted it. You should have highlighted it, the end behavior. If you need to make a note, you need to say end behavior, point to it, whatever you need to do. All right, extra credit opportunity. Number 3, let f of x equal 3 to the x power. What transformations of f result in exponential growth functions? What transformations would result in an exponential decay function? So, if you would like to, please write it on a separate sheet of paper and turn it in to where you would turn in your mastery checks. Okay, moving on. We're going to move on to example 2. Example 2, we're talking about exponential growth and decay, but in a equation form. So we have two equations. So let's see. Some real life quantities increase or decrease by a fixed % each year or some other time period. The amount of y of such a quantity after t years can be modeled by one of these equations. So our growth, notice they're the same. The difference is our growth has a 1 plus r, our decay has a 1 minus r. Note that a is the initial amount, all right, so initial amount, and r is the % increase or decrease. So this is important. A is the initial amount. R is the % of increase or decrease. Written as a decimal. Written as a decimal. All right. I know y'all love decimals. You hate fractions. Love decimals. All right. The quantity 1 plus r is the growth factor, and 1 minus r is the decay factor. So let's dig right into example 2. All right. The value of a car in y thousands of dollars, or the value of a car y in thousands of dollars, can be approximated by the model y equals 25 times 0.85 raised to the t power, where t is the number of years since the car was purchased. So we need to first determine, is this a exponential growth or decay? Well, if we look at our base, our b value is 0.85. All right, so if our b value is 0.85, would that be an exponential growth or decay? Well, since this is not greater than 1, it is between 0 and 1, it would be an exponential decay. All right, so that one's an exponential decay. All right, now we have to identify the annual % increase or decrease in the value of the car. All right, so because t is given in years and the decay factor is 0.85, we're going to take that and put it into our decay model. So 1 minus r, because remember that's written as, 1 minus r, that's written as a %, right? R is % of increase or decrease, written as a decimal. So if we take 1 and we subtract that 0.85, we get 0.15. So we can turn this into a percentage by 1, moving your decimal 2 places to the right, or 2, multiplying by 100. So our annual % of decrease is 15%. That is a 5. I want to just specify that that's 15 and not is. All right. So we know it's an exponential decay, and that it has an annual % of decrease of 15%. All right. Last thing, we need to estimate when the value of the car will be $8,000. So we are estimating. So what we can do is plug in some numbers and see what we get. All right, so we could take our equation. Remember, t is the number of years. So pick a couple and test them. So I don't know, where do you want to start? Let's say 5 years. Let's see where it is in 5 years. So let's test y equals 25 times 0.85 to the 5th power. All right, so we're just testing that. Going to put it in our calculator, see what we get. All right, so we have 25 times 0.85 raised to the 5th power, and that gives us 11.09. So if we look at that in thousands, that is $11,000. About 5 years, the car's worth $11,000. All right, they gave us, they ask in this, but they don't show it here. They ask us to determine when the value of the car will be about $8,000. I don't know why it's not written in the question, but I'm just going to put here after 5 years, because this became 11.09. So after 5 years, the car's worth about $11,000. All right. They do ask to find out approximately when is it $8,000. So I didn't realize that that wasn't written on this part, which is weird because I made these, but it didn't. I don't know why they didn't put it in the question. Anyway, moving on. So if we had to approximate when Y would be $8,000. So we want to find when Y would be approximately $8,000. So this one, that is the ugliest 8 in the world. This one was when the car was about 5 years. All right, so after 5 years, it's worth $11,000, and typically your car depreciates. That's why we have an exponential decay. So let's test another one. Let's try 7. All right, let's plug in 7 because I don't think 6 is going to bring it down enough. So let's try 7. So let's find out what is Y when T is 7. I guess I should have did squiggly lines with that one too. All right, so just going to plug it into the calculator. All right, so we have 0.25 times 0.85, and we are going to raise it to the 7th power. And if we move our decimal 2 places to the right, or you could look at it as multiplying by 100, we would get 8.01. So Y would be approximately 8.01. So that looks pretty good, pretty good. So we would say after 7 years, the car would be approximately $8,000. All right, so just a way to use this in real life. All right, I know you're never going to. That's what you always tell me you got calculators and Google for. All right, so I'm going to stop the video here, and we will come back on a new video.